Welcome to lesson number 3 of characteristics of a linear relation. And we're starting at lesson number 3, so we're skipping lessons 1 and 2. And we're going to start with just looking at the slope of a line. Now, a slope of a line, and let's take a look at this example here. But a trucker is driving up a hill with a heavy load, and they may be concerned with the steepness of the hill. When building a roof, a builder may be concerned with the steepness or pitch of the roof. And a skier going down a hill may be concerned with the steepness of the hill. In math, the term slope is talking about steepness of a line. So the slope of a line segment is measured in the steepness of that line segment. So it's a ratio, and the ratio is of the rise, or how much it goes up, by the run, or how much it goes over. And this gives us our slope, that dotted line. So rise is positive if you count upwards, and it's negative if you count downwards. And the run is positive is positive if we go right, and it's negative if we count left of the of our values. So let's look at a class example number 1, where we have each line segment on the grid with integer coordinates, and we want to complete this table below. So line segment AB, we are referring to this line here. We want to talk about the rise. So how much does it go up? Well, if we look at this rise, here's the run going this way and the rise going upwards. The rise starts here and goes up 2 units. So we would say that it has a rise of 2. And the run, we would say, has a rise of a run of 1, 2, 3, 4, 5, 6, 7. And so my slope here would be the rise, which is 2 divided by 7, or 2/7. Now let's look at line CD. CD starts here and goes down there. So this is going down, and it's also running to the left. So first of all, the rise is dropping. So we have a rise of 1, 2, 3, 4, 5, but negative 5, and a run of 1, 2, 3, 4, also negative 4 because it's going to the left. And if we go rise over run, that's negative 5 divided by negative 4, which would equal positive 5 over positive 4. And last we have EF. It is decreasing like this, and so we have a negative run and a negative rise and a positive run. So my rise here is going to be 1, 2, 3, 4, 5, also negative. But now we have a positive run, so 1, 2, 3. Now this is going to result in negative 5 divided by positive 3, which is going to stay as negative 5 over 3. And so here we have a slope that is negative. In this next example, we want to investigate the slope of the line segments. And we again want to complete the chart and write the slopes in simplest form. So AB, I'm going from here to here. And if we look at these little dots in between, that's how many units we're moving over. And so AB is going up by 1, 2 units, a rise of 2, and it has a run of 1, 2, 3. And so my slope here would be the rise, which is 2 divided by 3, 2/3. My next line, AC, so from A to C, let's see how much it goes up. It goes up by 1, 2, 3, 4, 5, 6, 7, 8. So a rise of 8 and a run of, so this was 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So when we divide this, 8 over 12, rise divided by run, we would then have to simplify this to lowest terms. And so 4 goes into both 8 and 12. It goes into 8 2 times, and it goes into 12 3 times. Excuse me. Now, from A to D, we have, if this was 8 from A to C, then we go up 2 more, and that would be 10, a rise of 10, and a run of 3 more than 12 would be a run of 15, or 10/15, which also simplifies to 2/3. Notice how it's the same triangle, so the slope is the same each time. And then from B to C, from here to here, we have a rise of 1, 2, 3, 4, 5, 6, 7, or sorry, 1, 2, 3, 4, 5, 6. And then a run of 1, 2, 3, 4, 5, 6, 7, 8, 9. And so we have 6/9. And if we divide both these by 3, we will also get 2/3. So how are the slopes of the line segments related? They are all equal. They are all equal. So the slope of a line, the slope of all line segments on the same line are equal, right? So this was the same line, and each segment, so from A to B, A to C, A to D, and B to C, they were all equal because they're on the same line. So the slope of a line representing the graph of a linear relation can be found by the formula slope is equal to rise over run for any 2 points on the line. Now we're going to take a look at investigation number 2. When we're going to consider the line segments in grid 1 and grid 2, and we want to determine the slopes of all the line segments in grid 1. Okay, so in grid 1, notice how there is no rise, it's just a run. And so our rise, we would say, is 0. And if we divide anything by 0, or if anything, if 0 is divided by anything, it's just going to result in 0. And so for grid 1, our slope is 0. And for grid 2, however, notice how it all has a run. All of these have a run. So we'd say like this one's got a run of 10, this one's got a run of 8, 12, and so on and so forth. So in this case, there's no run, only rises. And I think I was saying run before, but sorry, there's no run, only a rise. And that means we would be dividing these by 0. And if you divide something by 0, that results in undefined. And just a quick example for both, if I look at this line segment A to B, from A to B, this is 1, 2, 3, 4, 5, 6, 7, 8, and this would be A to B would be 0 divided by 8, which would just be 0. But if I look at from I to J here, that's 1, 2, 3, 4, 5, 6, 7. That's 7 divided by 0. And if you plug that in your calculator, you're going to get an error because it's undefined. Now we want to complete the following statements. If we have a horizontal line, so going side to side, line segments have a slope of 0. But if we have a vertical line segment going up and down, that would result in an undefined slope. Undefined. Now in this next example, or investigation number 3, we have each line on the grids, so grid 1 and 2, and it passes through at least 2 points with integer coordinates. And we want to calculate the slope of each of the lines. And so one thing to remember on this Cartesian plane, where we have 4 different quadrants, the rise is positive if we count upwards and negative if we count downwards. And the run is positive if you're going to the right, but negative if you go to the left. So let's complete the tables for grid 1 and grid 2. So for grid 1, line 1, let's find out what our slope is. Our slope, if we count 2 points on our line, and so right now it's a little bit more challenging to determine what our actual grid is like, right? Notice how this line is not actually on the grid, and so we would just identify 2 points that do fall on the grid. So I'm going to choose that point and this point, and notice how I choose these 2 points because they line up on the edges of the squares, right? And so those will be a little more helpful in trying to determine how my line is changing. And so if we look at this slope here, it has a rise of 1, 2, and it has a slope of 1, 2, 3. So it has a slope of 2/3. With line number 2, I'm going to do the same thing. I'm going to choose two dots or coordinates that fall on to the edge of the squares, and then I can count the rise and run this way. So this one goes up by 1, 2, 3, 4, 5. and it has a run of 1, 2, 5 halves. And then my third line, I'm going to choose this coordinate and this coordinate for the same reason. They fall on the edges of the squares. And this one has a rise of 1 and a run of 1, 2, 3, 1/3. Now, if we look at the other slopes for grid 2, line 4, I'm going to choose this coordinate as well as this coordinate. And you can choose different coordinates, right? You could have chosen this one as well. But anyways, we have a run of -2 this time. So we go down 1, 2. So -2, and we have a run of +3. So that's going to be -2/3. For line 5, I am going to choose this coordinate as well as this coordinate. And I have a run of 1, 2, 3, 4, 5 negative. And I have a run of 2 in the positive direction. 1, 2. And then line 6, I'm going to choose this coordinate here and this coordinate. And that's going to be a drop of -1 and a run of +3. And then we want to compare the slopes of these lines. So line 1 and 4. So here's line 1 and line 4. They are equal but opposite in sign. So equal in value but opposite sign. And that's actually for all of them. So they have the same value, but they just have the reverse sign. And so a line which falls from left to right, so falls from left to right, has a negative slope. Oh, sorry, a line which rises from left to right, so rises has a positive slope. I was reading that backwards. That's positive. And a line which falls left to right, like the ones in grid 2, have negative slopes. Now let's look at class example number 2. We have a grid, and this grid has been superimposed on a sketch, and we want to estimate the pitch or the slope of the roof to the right of the worker's head. So we're looking at this area here. And looking at this area here, if we want to estimate the slope, then again, it's best to do so if we're looking at parts of the grid that actually line up with the edges of the squares. So we want something that would be like right here. And so I'm going to be looking at this point and the next point that's on the grid, which is right here. And so if I look at that, remember the slope is equal to rise over run, or rise divided by run. And so we have a slope of 2, a rise of 2 and a run of 1, 2, 3, 4, 5, 6, 7. In part B, we want to think about, could the same grid be used to estimate the pitch of the roof the worker is standing on? And so that's this pitch here. And the answer is no, because we're looking at this. This is like this part of the roof is coming out at the z-axis, which we haven't discussed. But there's a third dimension that we don't use. But with the Cartesian plane, we're not looking at. We're only looking at the x and the y direction. But this part of the roof, this pitch of the roof, would be coming out like basically out of the page, and so it's not on the same plane. So no. I'll say that part of the roof, is not on the same plane. Is not on the same plane. In class example number 3, we want to draw a line segment on the grid which passes through the point -4 and 2, and it has a slope of -2/3. And so it's on the point -4 and 2, which would be right here. So -4, +2, and it has a slope of -2/3, which means it goes down by 2, 1, 2, and over by 1, 2, 3. So that's where the next point of our line is going to be. We want to write the coordinates of 3 other points on the line segment which have integer coefficients. And so if I, and sorry about the, my pen bled through on the other side. So I'll circle the coordinates I'm looking at. So I'm looking at that one. And this one also has a slope of -2/3. So 1, 2, 1, 2, 3. And I'll circle that one as well. 1, 2, 1, 2, 3. And I'll also circle that last one. And so we just want to write the points that these fall on. So this would be at -1 and 0. So one of them is -1 and 0. This one here would be 1, 2. So +2 and -2, x, y. And then 5 and -4. And 5 and -4. And our last example is class example number 4, where we have a line segment and it has a slope of -5/7. It has a rise of 12. We want to calculate the run as an exact value. And so in order to find the slope, remember slope is equal to rise divided by run. And we're told that that is -5/7. Now, it has a rise of 12, so I'm just going to substitute this word rise with 12. And we're looking for the run, and that's equal to -5/7. Now, if we think of run as x, then we can make an equation here, and this would be 12/x is equal to -5/7, in which case we just got to solve for x. Now, what I'm going to do is I'm going to multiply both sides by 7. So 7 times 12, we're going to end up with 84. and I'm going to continue it over here. But 84/x is equal to -5. And if I bring my x onto this side, but multiplying both sides by x, I'm going to have 84 is equal to -5x. And as an exact value, I would divide both sides by 5. And x would equal 84 divided by -5 as my final answer.